Okay, continuing some examples from 6.2. In the last video we looked at one-to-oneness for graphs. The next thing that we're going to do is talk about inverses. So the definition of an inverse, which we write as f inverse of x this way, is that f of f inverse is the same as f inverse of f, and they should be equal to x. So a function and its inverse should cancel out when you compose them. When you put one inside of another one, you should be left with just x, nothing else, not 0, not 1, just x. All right, so let's look at an example. Let's say we've got f of x equals x cubed minus 2, and g of x equals the cube root of x plus 2. We want to know, are they inverses? Okay, so we're going to look at f of g of x and g of f of x and see if they cancel out. So we do f of g of x, and that means that g is going to be on the inside, so we're going to take cube root of x plus 2, and we're going to put that into f. So it's going to go right here in f. We're going to have cube root of x plus 2. Okay, this is going to go in here, so we're going to have that cubed minus 2. Okay, so we've got the cube and the cube root. They're happening at the same time, so the cube and the cube root cancel out, and we get x plus 2 minus 2, plus 2 minus 2 cancel out, and we're left with just x. Okay, so we do f of g of x and we get x. That's the one part of inverses. Now when you test the other half, 99.9% of the time it's going to work out, but we'll go ahead and check it anyway. So g of f of x, this time f is on the inside. So we're going to take x cubed minus 2 and we're going to put it into g. So we're going to have cube root of, and the x cubed minus 2 is going to go right here. So we're going to have x cubed minus 2 plus 2 underneath that cube root right here. All right, so the plus 2, now we're under the cube root. The plus 2 minus 2 cancel out. We've got cube root of x cubed. Now those are happening at the same time, and that simplifies to x. Okay, so you do the composition just like we did in 6.1. Be really careful with your order of operations on simplifying, and if everything cancels out, you're left with x, then we say yes, they are inverses. Okay, moving along. So now we know what they look like. We know what one-to-one looks like. We know the definition of inverses. Let's look at what inverses look like on a graph and as functions. So inverses as a graph. All right, the key to inverses is that they have to undo each other. So in the video you should have seen, whoops, hold on. Okay, the basis of everything that we've done is that a function does something to x, it does something to your input, you land at your output. So you do something to x and you go to y. The inverse has got to undo that. That's why it's important for them to be one-to-one. We've got to make sure wherever f takes us, f inverse takes us back to our starting point, like a round trip ticket. All right, so x goes to y, and f inverse y has got to go back to x. So if you have a point on the graph that is AB, if this is on the graph of f, the f inverse has got to have the point BA. Okay, if f has the point CD, then f inverse has got to have the point DC. Okay, because the first one's your input, the second one's your output. So input to output, f inverse has got to take the output back to the original input. All right, so between a function and the inverses, the x's and y's literally just switch. So if you're looking at a graph, let's just kind of make a graph here. All right, so let's say this is 1, this is at -2. Let's write that as a point. Okay, 0, -2. This is at the point 3, 0. Let's give it another point up here. Let's say this is 5, 4. and maybe another point over here that's, let's say that's -3, -5. Okay, so this is our function. I just drew a picture. First of all, it's got to be a function, and it's got to be 1-to-1. So we see that it passes the vertical test, it passes the horizontal test, so this is a 1-to-1 function. So we should be able to find the inverse. So let's say that we want to find f inverse as a graph. All right, what we're going to do is we're going to use this idea that the x's and y's switch. So if we had the entire table for f, if we had the whole table of values, we could switch all the values and then graph f inverse. We only have certain ones here, and that's okay. We can go ahead and flip those. And then if you remember from the video, we also know that the graph is going to reflect across the line, the diagonal line y equals x. Oh, that point's off. Hold on, I'm going to have to change what this point is because it's not... 2, 3, 4... It's not really to scale here. Let me say that this is the point 4, 4. This is what happens when you just make up a picture. Okay, let's say that's the point 4, 4. Okay, so we're gonna reflect along y equals x. That's an effect of switching the x's and y's, and we're also going to switch all of the points. So start with the points that you know. 0, -2 is going to become -2, 0. We're not changing the signs, we're not doing anything else, we're just flipping the x's and y's. So this point is going to become -2, 0. This point, -3, -5, is going to become -5, -3. 3, 0, we reverse that, that's going to be 0, 3. And then 4, 4, when we reverse that, it's still 4, 4. So anything that's on the diagonal line, if you reverse it, it's going to be the same point, and it's going to stay on the diagonal line. So anything that's on the diagonal line is going to cross on the diagonal line. Okay, so we've got our points. Now we just need to mirror this across the diagonal, which is a little bit tricky. My advice to you is just to either go towards the diagonal or go away from the diagonal. So if I look, this point right here, compared to the diagonal, it's going away. So I'm going to do the same thing with my red. I'm going to go away from the diagonal. And then this part right here, see how it goes really close to the diagonal and then away? So I'm going to do the same thing with my red. I'm going to go really close to the diagonal and then away to the other point. It's okay if it doesn't look perfect. And then the next part kind of bows away from the diagonal very gently. So I'm going to bow away from the diagonal very gently. And then this part goes to the diagonal, almost in a straight line. I go to the diagonal. And then this last part crosses the diagonal and goes away from it. So I cross the diagonal and I go away from it. Oh, it's not going to go downhill though. All right, there we go. Okay, and now if you kind of turn your head, you should be able to see that we are fairly symmetric across the diagonal. It doesn't have to be perfect, but hopefully you get the idea there. Okay, so we've looked at verifying inverses, we looked at inverses as a graph, and now let's look at how to actually find the inverse. And we use this idea that you switch the x's and y's. So you should remember from the video there's 3 steps. 1 is to change to xy notation. So we want to get out of function notation, change to xy notation. 2, we're literally going to switch the x's and y's. And then 3, we're going to solve for the new y. Okay, so let's say that we want to find the inverse of, let's do f of x equals x squared plus 4. All right, and I'm going to have to put a little disclaimer on here. x greater than or equal to 0, you don't need to worry about that. We're just restricting the domain to make this 1-to-1 because a parabola is not 1-to-1, and therefore we'll have problems with the inverses. So we're going to restrict the domain that x has to be greater than or equal to 0. You don't need to worry about that. You don't need to come up with it. Just know that's what they're doing there, is they're making it 1-to-1 so that everything works. Okay, so step 1, we're going to change to xy notation. So we're going to go back out of f of x, back into y. Step 2, we're literally going to switch the x's and y's. So y becomes x becomes y. I'm not moving them, I'm changing what the letter is. Now you might want to make a mark here, because when you do that, first of all, that's not normal math. Second of all, this is now your new function. When you switch the x's and y's, you have created a different function. And you might want to note that, because you might have trouble when you go back later and look at it. So we switch the x's and y's, and then we solve for the new y. So I want to get the new y by itself. I'm going to do the opposite. So I'm going to subtract 4 on both sides. And then the opposite of a square is a square root. We've seen that before. So I take the square root on both sides. I get x minus 4 is equal to y. Now normally when we take a square root, we do the plus or minus, but we started off 1-to-1. We've got a restricted domain here, and we're going to finish 1-to-1. So we're only going to take the positive root, because if x is positive here, that means that y is positive as well. So just, again, don't get too bogged down in the details, but I just want to make sure you understand we don't do the plus or minus root, because we've got to end up 1-to-1 as well. So we're just going to take the positive root for all of these. Okay, if you're going on to calculus, that might be something that you worry about. Probably not until Calc 2, honestly. So for now, just make sure that you understand how to find it, and you can functionally do that. Okay, that should finish up 6.2.